2n plus 1. What? Not. We're not squaring it. We're adding them. So now let's multiply. This is going to be n squared plus n plus 1 minus n squared is 2n plus 1. What cancels on the left? And what are you left with? 2n plus 1 is equal to 2n plus 1. So is it true? It is true. Very cool. I like that. If you take any two consecutive integer squares and you square them and then subtract, what are you going to get? The sum of the two. Very cool. I like that. Awesome. Very cool. Exponents, but exponents and radicals are pretty much the same. This was, what does that equal? X to the 1/3. Exactly. Exactly. Those are radicals. So have you actually learned about radicals? Absolutely. The important thing to know about radicals so far is how do you manipulate them, and what's the key thing that you have to have in common between two things in order to multiply them or divide them? The base. You really like, we love common bases. We love them because it makes things nice. It doesn't make it impossible if you have different bases, but do you remember we did something yesterday where it was like, 10 to the 8th times 2 to the 8th? Well, that equals actually 10 times 2 to the 8th power. That's fine. But what happens if I want to rearrange that? What is 10? 5 times 2 to the 8th times 2 to the 8th. And what can you do with that exponent right here? 5 to the 8th and 2 to the 8th and 2 to the 8th. So that's 5 to the 8th times 2 to the 16. That's another way to do it. This, in a way, could be argued as the lowest, like the most common form, because can you break down 5? Can you break down 2? They are both there for what? Prime. This would be called the prime factorization. Now here's a real tough question for you. This is actually kind of trickier than it looks. This is a big number, do you agree? Real big number. Can someone tell me one of the factors? 2. What's another factor? 5. What's one other factor? 7 is not a factor. 1 itself, 5 and 2. Are there more factors? There are tons of other factors. Give me one other. 4, 8, 16, 32, 64, 128, 256, 512, 1000. Why did I list all those? Yeah, you have 2 to the 2nd, 2 to the 3rd, 2 to the 4th. These are all factors. Why are these all factors? Yeah, they are divisors. You can divide these evenly into there. There's lots of them, right? Then there's also 5 to the 1st, 5 to the 2nd, 5 to the 3rd, 5 to the 4th, 5 to the 8th. And every possible combination of those things. 5 times 2 to the square, 5 times 2 cubed, 5 times... So there are a lot of factors. Yes, but this is a nice prime factorization because all of those other numbers, are they prime? No. What are the only prime factors here? 5 and 2. Going to the prime factorization is useful.
What a polynomial is.
Okay, so I'm just curious. I'm trying to understand the psyche of teenagers. And it's like a constant, never-ending struggle. I'm just curious. I'm going to get this on the record. So you ran into this one, like, what is a polynomial? What did you do when you... Okay, you're supposed to come up with an interesting fact about a polynomial. So I'm curious. What did you do when you ran into it? I don't know what a polynomial is. What did you do? Google it. At a minimum, like... Seriously, at a minimum, like an 11-month-old child could Google this. They don't even know what letters are. Just like copy the two, okay? Google it at a minimum. If that doesn't get you anywhere, there's many other things you can do, but probably will you get a lot of places to start if you Google polynomial? Yeah. Literally, let's just see what comes up, shall we? Ready? We shall. Ready? How about this? What is a polynomial? Question mark. Polynomial math is fun. Divisions, valuation. There's lots of them, right? Consisting of several terms, right? You could even have it. Ooh, cool. That's really cool. So look, Rene Descartes. Let's say this one too. Oh, come on. Say it for me. Ah, oh, dang it. That was really cool. Oh, you can? Anyway, lots of different things. We could also... I've only shown you this a bunch of times. It is. What about...
No.
Is that a polynomial?
No, it's not finite because pi never ends.
Finite number of terms.
Oh,
Yes.
How many terms are there?
there's
3. It ends. Finite number of terms, and what are the powers? Oh, they're all positive integers, aren't they? There's actually x to some power here. What's the power of x right here? 0. Correct. Dway. Very good. Pi is not an exponent in here. It's not an exponent. It's not an exponent. It's not an exponent. It's not an exponent, right? So the coefficients can be any real number. Yes. If there was nothing there in the first place. There's an invisible number. X to the 0 is 1. So you can say it's invisible right there. R, the coefficients are just real numbers. So what are the only things the coefficients can't be? Imaginary numbers, something with I in it. You don't even know what that is. So if you saw this,
Is that the only imaginary number?
yes, it's the there's an infinite number of imaginary numbers, but they all have I in them. Say that again. Overall method that you use, Missy. Each term in one by each term in the other. I think that's what you said. Exactly. Now, you the first time you see that, you probably see a word associated with this. First, outer, inner, last. Many of you have seen that. It's not really accurate anymore because how many terms can you have?
6.
Yeah, there's no first and outer. There could be a first and outer, but could there be lots in between? Absolutely. Okay, you ready for your really